Okay, I've updated the Canvas folders for today as well as Wednesday. And I did put a video before the reading assignment for Wednesday. And Wednesday, we may or may not finish chapter 6. We'll see. But what I wanted to do today was, since we'll go back here, since the reading assignment for, I think it was last time I kind of switched them up, was to look at physical properties of enantiomers as well as diastereomers. I figured I'd do that with kind of what we're going to do in lab in the next couple weeks, as well as some practical stuff that I've had research students do in the past. So, I'll just show you where, if we ever get there. All right, so here's what all right, so I'm going to talk about the differences in physical and a little bit of chemical properties in terms of enantiomers and diastereomers. So the only physical property that a pair of enantiomers have is how they interact with plane polarized light. Now, by enantiomers, I mean the two molecules that are different, that are non-superimposable mirror image isomers. And what we saw last time was that when you have more than one chiral center, there's only one enantiomer, and then there's a whole bunch of diastereomers. So we're going to start with enantiomers. So the first question is, what's plane polarized light? And what you have to realize with light is that, oh good, it's not even going to let me draw. All right, so here's plane polarized light. Normal light, bless you. We know that, or if you've had basic physics, you know that basically light travels as a wave. And also from general chemistry, you would know that. Well, there's two vectors that make up light. There's a magnetic vector and there's an electric vector. And so those vectors, basically, if we looked at them in 360 degrees, those vectors would be in all 360 degrees for non-polarized light. So what we're seeing from the fluorescent lights, those vectors would be oriented in all 360 degrees. The problem is that we need to select one orientation. And so that's where we use a polarizing filter. Now, if you have decent sunglasses, they'll have polarizing lenses in them, such that if you were to look at, sometimes when you look at the sun on water, you can kind of see it shimmer in some places, but not in others. That's because light that bounces off an object is also polarized. So they are also polarizing filters for cameras, so that if you're going to take a picture of a car, you might have the light come off, and then you could kind of adjust that so that there's no reflection. So what it does is it acts very much like a picket fence. You know, the picket fences are the ones with the slats in between it. So what it does is it basically, the polarizing lenses allow only one orientation of plain polarized light to pass through it. So once we have the ability to create plain polarized light, then we can pass it through our sample. And our sample's typically dissolved in a solvent. So what happens is the chiral sample, meaning one of the enantiomers, will interact with that light to cause it to rotate, so that the light has rotated some number of degrees that we call alpha. And that's how we know that the molecule, that we have one enantiomer of a molecule, is that the plane polarized light gets rotated. Okay, and this was done back in the 1800s by Pasteur, Louis Pasteur, who invented milk. I made that joke when I taught at Kansas State, and afterwards in the smoking section that happened right outside the building, they're like, you know, he really didn't invent milk. And I said, I know, it was a joke. But Pasteur did a lot of things, but one of the things that he did was he took crystals from caps of wine, and those crystals, you could actually put them under the microscope and you could see that there was a left and a right-handed version. And so he could, there's a video that says, as he painstakingly separated them with tweezers into two groups, the left and the right-handed version, he then put them in water, used plain polarized light, and showed that they rotated. Then he also showed that the other version rotated the light in the opposite direction. So the first thing is that plain polarized light will interact with chiral molecules and it will cause them to be rotated. The question is, how is it going to be rotated? Is it going to be rotated to the left or the right? And what's the exact rotation? So that observed rotation that we see is dependent upon these four things. It's dependent on the exact compound that's used. So in other words, each enantiomer has a unique number of degrees that it will rotate plain polarized light. But it also is dependent on the length of the sample cell. So the longer the cell, the more the light interacts with it, and the more that it rotates. And then the concentration of the sample, the more compound that's in there, the more it interacts with the plain polarized light, the more that it rotates it. The solvent isn't as much of a deal as it's just listed there. Usually we have to list the solvent we use to make the measurement, but it really won't matter. So the two important things that we have to factor into this is the length of the sample cell and the concentration. Because what I'd like to do is to create a physical property called specific rotation that is unique to each chiral molecule. But I can't do that if somebody uses a 10 centimeter cell and somebody else uses a 20 centimeter cell. And I can't do it if somebody uses one concentration and another. So what we do is we basically create a formula that will help us. And so basically if you double the cell length, you're going to double the amount of rotation. And if you double the concentration, you would see double the amount of rotation as well. So here's what's called the specific rotation calculation. And I think you need to do some of these calculations in the reading as well as the homework for Chapter 6. So what we have is we have the specific rotation is in brackets. It has a 20 and it has a D. The 20 stands for the temperature, and the D stands for what's called the D line of sodium. So we have to use a very specific wavelength in order to make this measurement. We don't necessarily have to, but for a really good reading, we have to use this D line of sodium. It used to be in the old days when you had the electric, when you still have electric lamps, street lamps, but a lot of those are being replaced with LEDs now. It used to be that they used a sodium vapor lamp. And so it's kind of an orange color is this D line. So basically the specific rotation is equal to our observed rotation divided by L, which is the cell length. And the cell length is typically measured in decimeters. And so 1 decimeter equals 10 centimeters. And typically when you buy these, you either buy them in like a 1 decimeter cell. So that way it cuts down on the math. Because this is organic chemistry, and so we try to avoid as much math as possible. The concentration is the grams per milliliter of sample. And you might say, well, why not a molar concentration? Oftentimes, we don't know what the molecule is. And so if we don't know what the molecule is, then we can certainly prepare a solution of so many grams per mil. So that's how we measure the specific rotation. And we're going to do this in lab a couple times for the rest of the semester. We're going to do it when we use yeast to make a product that will be not 100% of one enantiomer, but it'll be like 85-15. So we'll measure that rotation to see what the major product is. And then we're also going to take naproxen, the active ingredient of naproxen, and we're going to both use the salt, the sodium salt where the carboxylic acid's been deprotonated. We're going to measure its rotation, and then we're going to convert it over to naproxen, the carboxylic acid, which is what would happen when it goes into your stomach, and we'll measure that rotation as well. So you're going to get practice with these equations in lab, but you also need these equations for the Chapter 6 homework problems. Okay, so that's the specific rotation, and basically that means that for a molecule, anybody should get the same specific rotation if they factor in their cell length and their concentration. So it creates a specific, unique physical property for that enantiomer. And ultimately, we could use that to determine the purity, which I'll talk about in a couple minutes. So here's an example. This is the structure of naproxen sodium. Over here, the COONA is a carboxylic acid that's been deprotonated, and sodium ion's a counterion. The chiral center is right here. So there's one chiral center for this molecule, so it can exist as R or S. It can also exist as D and L, because we didn't define D and L, did we? So let's go back. So when the rotation is positive or clockwise, that enantiomer is called the D, which is the dextra rotary. And then if the rotation is negative, which is counterclockwise, that is called lever rotary. So we have the D and the L that we can use now to describe the enantiomers. So the enantiomer is the handed form, and it could have one chiral center, it could have 20 chiral centers. What we're talking about is we're talking about just the two enantiomers of that molecule. Not diastereomers, but the mirror image that one molecule has with the other. So one is the dextrorotary, one is the lever rotary. And those are independent of chiral center. So, in other words, if you have one chiral center, you know that the chiral center is either R or S. But that's the configuration. That's the exact three-dimensional structure around that carbon. The D and the L is a molecular property. And there's no correlation between R and S and D and L. And what I mean by that is some R molecules are D, and some R molecules are L, and vice versa. So you can easily determine D and L using this instrument that's called a polarimeter, where basically you place the solution, shine the light through it, and then use polarizing lenses to figure out how much the light was rotated in degrees. You can determine that for an enantiomer, but to get to whether the chiral centers are or S is much more difficult. Much more difficult. And what you have to do there is you have to create the molecule pure, determine if it's D or L, and then you have to precipitate it slowly from solution so that you get what's called a single crystal. Like a single crystal would be what salt looks like coming out of the salt shaker. If you looked at it, it would be cubic. These crystals have to be perfectly shaped, perfectly clear. On the molecular level, it's like taking a shoebox and putting a model into it, and then stacking shoeboxes in 3 dimensions, where every shoebox has exactly the same model in exactly the same position in each of the shoeboxes. There's no atoms that are slightly moved in either direction. That creates what's called a crystal and a perfect crystal. And then if you pass an X-ray beam through it, that crystal diffracts the beam into many small beams, and from the intensity of the beam and the geometry of the beam and some mathematics, which everybody does on a computer nowadays, we can actually put the structure back together and show, if we're lucky, whether it's R or S. I did crystallography for 2 years as a postdoc at Brown, and we never got to that point. But when I was at Duke as a graduate student, the X-ray crystallographer there was actually, he worked in, he was from Scotland, and so he worked with the guys that actually developed the whole technique. So he was amused that I was, as an organic chemist, going to do crystallography because that's not an organic field. And so he would give me insight in terms of how it's done. And that was one of the big problems is it really takes a great crystal to get R and S, to get the exact three-dimensional structure. But yet, if you're going to take and make a chiral drug, you have to show that to the FDA. So there are people out there that are trying to get the perfect crystals of their drug so that they can get the RNS configuration so that they can move it to the next step in their FDA trials. And he was actually a crystallographer that did Taxol, which at the time was a up-and-coming cancer drug. It's now routinely used. I think I've showed it to you. It's a big, huge circle of carbon atoms. But he would always get drug molecules from pharmaceutical houses, and they would say, well, this one's R. And he would routinely find out that's not. And then he'd have to go back and tell them, no, it's not R, it's S. But he was really good at what he did. And like I said, he was amused enough that I was going to go and do a postdoc in this, that he gave me some valuable insight. But that's the difference between the sort of molecular property of DNL and the really atomic property of the carbon RNS. But there's no relationship between them. So you have to determine that for each molecule. So here is our naproxen, which we can buy, so all this stuff's been done on it. And what they find is, or at least what they report is, that the naproxen sodium has a specific rotation from minus 15.3 to minus 17 degrees. Now, I find that a little troubling, that for a molecule that they need to know the exact specific rotation, they only give a range, which means somebody's either not giving you the exact number, or that there's a lot of error in the measurement. And there's a lot of error in the measurement. So we'll get to how they're going to actually determine that this Aleve tablet is only one enantiomer in a couple minutes. So when we buy the Aleve, I believe it rotates negatively, which means this is the L form. So we take the L form of Aleve if we take an Aleve tablet. The D form has some kidney toxicity issues, and so technically it should not be there. This should not metabolize in the body to the D form, which it will not, because the chiral center here is a carbon with a methyl group and the carboxylic acid. That molecule will not racemize, and it'll become a little bit more apparent as we move through the semester why that's not the case. So this is a pretty good drug in terms of if we can make it 100% pure in the L form, then it'll take care of my headache or my pain, some of my pain, but it won't destroy my kidneys. Okay. Now, you can use this specific rotation and actually measure the rotation of a product and determine what its percentage of R and S or its percentage of D and L is. It really should be D and L that we're determining the percentage of. And that's if we use a concept called enantiomeric excess, which is in the book, and they talk about this. Basically, the enantiomeric excess of a mixture is the percent of the major minus the percent of the minor. Okay? And so if I had something that was 75% D and 25% L, conceptually you can think about this as, okay, that 25% of L is, oh wait, we haven't talked about that yet, have we? This is not my best set of slides, apparently. Okay, this is not my best set of slides. I was going to say that the 25% of the L cancels out 25% of the D, but I haven't explicitly said that. So let's take a step back here. When you have D and L, since those two molecules rotate plane polarized light in opposite directions, when they're both present in the molecule, they will cancel each other out. And what Pasteur found when he separated his crystals into the left and right-handed forms was that when he made solutions of equal concentration of both of those, he got 0 degree rotation, is what he found. And that, a 50-50 mixture of the D and the L forms, is what's called a racemic mixture. So 50-50 D and L mixture will cancel each other out so that you will get 0 degree specific rotation. And that's called a racemic mixture. And I'm not quite sure where the racemic mixture comes from, other than I think there was a third type of crystal that always showed up on the corks of the wine, and it was called racemic acid. We actually now know it as tartaric acid. But what he found was that those crystals actually, they had a mirror plane that could cut through them, so they themselves were not chiral objects. And when he put those in solution, they had 0 degree rotation. So I suspect racemic mixture came from that racemic acid that was found in the... This is all done with wine crystals, with crystals that were found on the corks of the wine, because Pasteur was in France. So if you have a 50-50 mixture, we're going to call that racemic mixture. So going back down here then, that means that 25% of the L will cancel out 25% of the D, leaving 50% of the D in excess, is the way that we use that term. So 50% enantiomeric excess basically means that you need 2 numbers that add up to 100, but then when subtracted equals that percent enantiomeric excess. So there's lots of ways you can solve those 2 equations simultaneously. But that's what we're looking for. You can do it in your head by just starting to guess numbers. You can add them up, where if I add these 2 equations, I now get 2x equals 100 plus then my enantiomeric excess, and then solve for the major component. And then the minor component is going to be 100% minus the major component. There's lots of ways to do this equation. I do not believe I used an easy method in the next slide to do that, but we can. So ideally, if you're going to sell a drug, you better be able to get it to at least 99 point, how many ever 9s after that you need to satisfy the FDA. And it's more than probably 3. So you need it to 99.49s in enantiomeric excess. That level of purity cannot be analyzed by optical rotation. And so I'll show you the method that's routinely used to determine what the enantiomeric excess or what the percentage of R and S or D and L molecules is. But it's not optical rotation because it's not sensitive enough for the purposes of drug approval. So let's say, for instance, that I had the specific rotation for naproxen sodium is minus 16. So that's somewhere in between their minus 15 and minus 17. And if you had a mixture that had a specific rotation of minus 12, what is the overall enantiomeric excess of the molecule. Now, the first question is, what's the major component? Is the major component the plus enantiomer, or is it the minus enantiomer? From just those two pieces of data, minus 16 and minus 12. So what's the major component? Minus or plus? Minus? Why? Because this one's minus. And that one is as well. So in other words, minus 12 means that the major component is the L form. Because these two numbers, if this was not minus, how could you have the minus being the major component? So the major component is always the sign. The major component is always the sign of the mixture's rotation. So that means the major component is L. So here I have basically kind of a larger equation, but we can do this like we did before. So in other words, the percent of the L form minus the percent of the D form equals the percent of enantiomeric excess. And then the percent of L plus the percent of D has to equal 100. So our question is, what's the percentage of enantiomeric excess? And to determine the percentage of enantiomeric excess, it's going to be minus 12 over minus 16 times 100. That's the percentage of enantiomeric excess. It's what's left over. So it looks to me like 4 degrees basically got canceled out. So we take minus 12 over minus 16, which is what? 6 over 8, which is 3 over 4, which is 75% enantiomeric excess. And I must have wanted to make the math really easy on this, because if you have a percent enantiomeric excess of 75%, no, the last problem was 50%. So now I need two numbers that when you subtract them, when you add them, add up to 100, and when you subtract them, you get 75. So if you don't want to simultaneously solve equations, which you could do by, whatever method you know, the linear algebra method would be great with determinants on the top and bottom. But okay, let's start out with, I don't know. How about 8515? 8515 would give me what kind of percent enantiomeric excess? 85 minus 15? 70. Okay, so it's a little higher than that. So let's go 90-10 is 80. So that's somewhere in between. I don't know. It's going to have to be let's see. 88-12 is what? 76. 87.5 and 12.5 would be 75. So there's your enantiomer. There's your percentages of L and D. Like I said, if you don't like that, you can use these two equations and solve it simultaneously. But I usually just choose something and then hone in on it. particularly at 8 o'clock in the morning after fall break. Then we don't have to use our serious math skills. So that's how you determine enantiomeric excess. Right. Is everybody kind of with me so far? Because you'll have to do this in some of the textbook problems. Not very many, but a couple, just to introduce this term. This term is huge in synthetic chemistry. If people are trying to make chiral molecules, they always report their percent enantiomeric excess. And you've got to get it to like 95 or better before anybody will take that reaction seriously. Which is kind of strange, but that's the way science has moved. It used to be, 70%? That's pretty good. Now it's like, no, that's not useful. You got to give me 95% or higher. And if you got drug discovery and you want to do make a chiral drug, it's got to be 99+% enantiomeric excess. All right. Same slide. So the nice thing about enantiomers is they all have the same physical properties, except for that rotation of plane polarized light. But that's a problem. If you think about you're in a drug company and you know this enantiomer will do whatever positive you need it to do, whether it's stopping somebody's pain to curing cancer. When you know you have that enantiomeric form, how are you going to make it? Or if you make it as a 50-50 mixture, how are you going to separate the two enantiomers out? Okay? Well, in order for us to do that, we need to understand the physical property differences of diastereomers. So diastereomers are completely different chemical compounds. They have different chemical and physical properties, and they can be separated by recrystallization, GC, TLC, column chromatography, etc. And here's an example of two diastereomers and how their melting points are different. So the first one is pseudoephedrine. That's what you take when you have a stuffed up nose. You have to go back to the pharmacist, show them your driver's license. You can only buy like 3.6 grams of pseudoephedrine a day, according to the Methamphetamine Control Act of like 1990 or something like that. And the pseudoephedrine has a melting point of 60 degrees. Ephedrine, which you cannot get because that was in diet supplements like fen-phen, that basically this is a molecule that causes your heart to beat faster than it should until it can't keep up and stops, which is not a good thing. This is the enantiomer, so in other words, or the diastereomer. These two chiral centers are opposite each other. And I know that because one's bold and one's dashed with the OH. And then the H has the opposite wedge. So those two chiral centers are opposite each other. And these two chiral centers have the same orientation, so they're the same. So if you remember back to Wednesday when we were talking about diastereomers, we said diastereomers have one chiral center the same and at least one chiral center opposite. So that's the case here. One chiral center is the same and one chiral center is the opposite. Ephedrine melts at 37 to 39 degrees. If I had a mixture of these and I shot them into the GC, which is probably done every day in the crime lab, given the fact that these two can be precursors to methamphetamine, which is apparently on its way out, in favor of opiates that just don't kill you slowly but kill you immediately. When you shoot these into a GC, you're going to see two peaks because they are different molecules. They have different physical properties. They also have different chemical properties. So they affect your metabolism differently. So those diastereomers can be easily separated, but enantiomers can't because they have the same physical properties. So if you want to physically separate enantiomers, you have to somehow convert those into diastereomers. And if you can do that, then you can separate the diastereomers and then somehow do another chemical reaction to get back your original two enantiomers after you separated them and put them into two different jars. So the classical method is what's called Mosher esters. And we'll talk about this esterification reaction later. But basically, what Mosher did was he had a chiral carboxylic acid. And if you had a mixture of enantiomeric alcohols, what you would do is you would react this one configuration of the carboxylic acid with the mixture of alcohols, and you would end up making two esters. One where the chiral center was the same, and one where the chiral center was opposite. So those two were opposite in configuration. Those two centers are the same. And so what you would make is you would make a set of diastereomeric esters. And then what Mosher was able to do was to use a column and separate these two esters out, put them in two separate test tubes, and then he has separated basically the enantiomers. Then what you have to do is then you got to get your alcohols back. So we'll find out later on that this reaction is called hydrolysis. So if you take an ester and you react it with base, you end up splitting the ester apart into its alcohol and its carboxylic acid components. And so now you have the two alcohols in separate test tubes by converting them to a diastereomer and then separating them and then converting them back into the alcohols. So this was the classical method, which worked and made Mosher at least famous for this topic. Now that's not how we do things nowadays. Nowadays we usually do this instrumentally. So I'll give you a very quick example here of how we can analyze molecules for their R and S and D and L components. So in essential oils, not clove essential oils, I don't believe, but in essential oils there's this molecule called linalool. And there are two chiral forms of the linalool. There is an R- and an S+. The R- has been described as flowery, fresh, and lavender-like because it's in lavender. And the S+ is herbaceous, musty green, having a citric note. Now, one of the problems with smell and fragrance is that there is no way to describe it other than with words. You cannot copyright or trademark a fragrance, meaning the fragrance that your nose picks up, because it doesn't have a physical representation. You can copyright music because it has a physical representation in the notes that you can put on paper. But a fragrance doesn't. You can copyright the name of it, but you can copyright its formulation, which most people don't. Most companies don't do that because then people would be able to figure out what they're doing. So they just keep them as trade secrets. And places like Chanel that make the high-end perfumes basically control everything that comes into their operation. They grow their own plants, etc. They make sure they have everything under their control. But I digress. So, one of the projects that is done actually in instrumental analysis is to analyze the percentage of linalool in different essential oils. So I went out, it was probably like eight or 9 years ago, bought everything, all the different essential oils that I knew had a little bit of linalool in them, and what we found was that 4 of them had the highest percentage: whole leaf oil, whole wood oil, rosewood, and coriander have the highest percentage of linalool in them. And then it drops off as you go through all of these. And I have boxes of essential oils that I got as part of this project. Well, if you want to analyze how the percentage of RNS linalool that's in the molecule, you need to use what's called a chiral gas chromatography column. So what happens in this case is that the column actually has one enantiomer of a molecule called cyclodextrin that's attached to it. And so if you take a column that has one enantiomer of that chiral molecule attached to it, what will happen is as the linalool passes through it, when the plus linalool interacts with the plus cyclodextrin, and when the minus linalool reacts with the plus cyclodextrin, you've now made 2 diastereomers. And so the plus and minus linalool have different affinities for the column because now the column is chiral. Think of it as maybe not a chemical reaction, but an interaction, like my left and right-hand glove analogy from last week. So what happens then is that if you use a chiral column, you can take a racemic mixture of linalool and you can pass that through the column and you will see both enantiomers come out. But then if you buy the minus, the pure minus, you only see one peak, and they didn't sell me pure minus because there's a little tiny S plus peak there. Now if I related this to drug discovery, this is how you could determine 99.99 something percent pure. This would not be pure, the bottom one. Okay, so we can then go through and we can take a look at the different kinds and say, oh, well, the whole leaf is essentially pure. The whole wood is essentially pure. Now this is a tree and a leaf that is found in China. Rosewood is controversial because rosewood comes out of the South America. You're not supposed to be cutting down the trees and selling them. Rosewood is used for guitars, and I think the government went after one of the guitar companies because they had undocumented rosewood wood that they were using. So rosewood turns out to be a mixture of either plus or minus in different forms. It's never 50-50. It's always one or the other. Coriander is always the S plus with a small amount there. So I could use this information to actually track the authenticity of those essential oils. And we did that. What we found was there were some manufacturers that were selling things that were like 100% R minus for their rosewood oil, and so that means that they're using whole wood oil and not rosewood oil. And I don't call them up and go, hey, do you know that your stuff you're selling is not authentic, because my legal team doesn't think that's a good thing to do. But they don't know because they're getting sometimes these things in 55-gallon drums. But we can use that chiral column now to determine what the percentages of those different compounds are. And again, what am I doing? I'm using the basic principle that diastereomers I can separate, but enantiomers I can't. So with chiral GC is how most drug companies would be showing that they have 100% pure material. Okay. All right, so on Wednesday we will finish up, or try and finish up, the chiral centers. If we do make it that way, then that means the problem assignments will be due next Monday. But if not, they'll be due next Wednesday. Right. you have questions as you're doing things, let me know by email or come see me.